Hello, this is Mr. Craig, and this is the 20 to make 12 quiz again. This is period 2, and again, I can't overemphasize enough, please take this quiz before watching the video. I know that in the other videos I've discussed quite a few items over and above what was asked of the question itself, but I really want you to take the quiz before you watch the video so that you can have an opportunity to make a few mistakes and learn from those mistakes. The key here is to not make so many mistakes, but if you make a mistake, learn from your mistake and don't repeat the mistake. Alright, well, let's get started here. Question number 1 says, refer to the following combinations, enthalpy and entropy changes for a chemical reaction, where we're given our sets of conditions here, where we have delta H is greater than 0, we have delta S is greater than 0. So let's go ahead and put the signs on these for each of the letters. And then we can go ahead and indicate the sign for delta G, even though delta G is not given here. And when we talk about delta G, this equation, again, I can't emphasize enough, be sure that you have this equation memorized, because on the multiple choice portion of the AP exam, you're always going to be asked a lot of conceptual questions about this and not have to do any calculations. Alright, so looking at A, what this is saying is that the hydrogen, I'm sorry, not the hydrogen, the enthalpy has a positive value and it's endothermic. The S has a positive value and it means that it's increasing in the disorder or in the entropy. So the only way that we're going to have delta G be negative under these two conditions is at very high temperatures. Okay, now what is high? Well, it depends on what the values for each of these are. But again, temperature is a key component in making delta G negative here. In B, again, we have delta H is greater than 0, so that means it's a positive sign. However, we have an organized system here, and the bad news is, regardless of what the temperature is, delta G will never, ever be negative, no matter what the temperature is. So the B is a bad situation. Let's just put a frowny face on there right now, because we don't want our chemical reactions to have to undergo the conditions for B. C, we have a negative sign for our delta H, which systems really like, and delta S is positive, and delta G will be spontaneous or negative at all temperatures under this set of conditions. So again, delta H is negative, delta S is positive, delta T, Kelvin, will always be a positive value, so having a positive delta S makes it back into that negative. So every single temperature, delta G will be negative. So that's a good situation. That's a very happy face there. Delta H for D, again, is negative, and S is negative. So for us to have a negative delta G, we have to have low temperatures here. So that doesn't merit a smiley face or a frowny face. That's kind of one of these faces. Okay, not really sure what to do there. E, delta H equals 0. We could have a change in energy where it's equal to 0. And S is 0. Actually, I've never even discussed that scenario before, but that is a bad deal. So if we have delta H is 0, has no positive or negative sign, but if delta S is negative, what can delta G be? It can only be positive. So that really is a frowny face. So that might be a situation where it actually cancels each other out, because even though I've never talked about the scenario with E, because we really don't have delta H's where we have a value of 0 too often, but it could happen. Alright, well, let's get to the questions. Number 1, must be true for a reaction is spontaneous at all temperatures. We answered that one, so whatever delta H is delta H is negative, delta S is positive, so I believe that was C. So number 1 should be C. And it is. Alright. And I said no for all the situations, and we just talked about that. True for the evaporation of water at 25 degrees in 1 atmosphere. Remember that when we're talking about an evaporation process, even though the temperature is the same, for water to evaporate, it has to absorb energy, which means that delta H will be endothermic. It's going to absorb energy. And we know that it does take place at 25 degrees, not at a very quick rate, but we do know that it takes place. So we know that the entropy is increasing. So we have two positive signs. So our two positive signs is our first scenario, should be letter A. Okay. And there's my explanation. So again, it goes from a liquid to a gas. That's why this delta S is a positive sign. All right. 3, true for the combustion of liquid propane to form water and carbon dioxide. Well, we do know that delta H in this case is exothermic. If we write out the balanced equation, I'm trying to do that quickly here, C5H12 plus O2, yields water and carbon dioxide. Let's see, so we'll have a 5 there, and a 6 there. So that gives us 10, 16, so 8. So we go from 9 to 11 particles. So that means that delta S is becoming more disordered or more random. So we have a scenario where this will take place spontaneously. So true for the combustion of pentane, where we have negative, so whatever that one was. I think that's the same one as C. Yep, so we have that one again at all temperatures. Okay, so 3C. Yeah. Now, do remember, or do recall, especially on these machine gun type questions, we can use an answer more than once. So don't freak out and say, well, we already used that one. Why are we doing it again? Sorry, guys, that's not me doing it. It's the people making up the test. But do know the scenarios. Okay. All right, number 4. The reaction below represents a precipitation reaction. And I think I haven't corrected this reaction. I think you have two possible answers. It could be A or B on this. So I actually apologize for having two scenarios here. Probably B would be the best choice. Hopefully a lot of people recognize, oh yeah, we've got lead with some ions forming a precipitate. So I apologize. Either of those would be the correct answer. Okay, so I will fix that definitely for in the future. Number 5, in solid methane, the forces between neighboring methane molecules are best characterized as, and whenever you see a question like this, draw the Lewis structure first and foremost, especially if it's talking about IMFs. Okay, IMFs are intermolecular forces. And when we talk about intermolecular forces, we have to know what type of compound we have. And there's two different types of compounds. There's polar compounds and there's nonpolar compounds. And when we talk about polar compounds, these are the types of compounds that can dissolve in water. When we talk about nonpolar compounds, these are the type of compounds that cannot dissolve in water. So they have to dissolve in other nonpolar substances. Probably one of the most important statements is like dissolves like. Okay. Now when I say like dissolves like, what that means is polar compounds dissolve other polar compounds, nonpolar compounds dissolve other nonpolar compounds. So when we look at methane here, okay, what type of compound do we have? Polar or nonpolar? Hopefully you said it's a nonpolar compound. So when we talk about nonpolar compounds, we only have one type of intermolecular force to deal with, dispersion, or London dispersion forces. When we talk about ionic bonds, we're talking about ionic compounds. When we talk about covalent bonds, we're talking about these type of bonds that are between atoms. So covalent, when you hear the word covalent, you better be thinking about sharing. And we have two different types of covalent bonds. There's polar covalent bonds and there's nonpolar covalent bonds. So covalent deals with sharing of electrons. There is no sharing of electrons with intermolecular forces. It's an electrostatic attraction between a negative end and a positive end of two different molecules. And these could be partial charges or full-blown charges. Okay. Hydrogen bonds, we have to have a polar compound, and we also have to have NOF. Now, what NOF is a hydrogen is attached to a nitrogen, or a hydrogen is attached to an oxygen, or a hydrogen is attached to a fluorine. Now, here's where the big mistake comes into play. It's like, well, I thought they were intermolecular forces. Why are they sharing electrons? These guys are sharing electrons in a polar covalent bond. However, between compounds, we have to have this criteria met for there to be that stronger hydrogen bond that takes place between two molecules. Even though we have to have these guys touching each other. If they're not touching each other, then it's just a regular old dipole force. When we talk about an ion dipole force, we're looking at an ionic compound and a nonpolar compound, which typically is like sodium sulfate. Okay, so we have an ionic metal and we have a polyatomic here, so we have some ionic dipole forces. All right, intermolecular forces. Know the difference between intermolecular and intramolecular. And intramolecular is between atoms. Alrighty. Number 6. Okay. Which of the following shows the correct number of protons, neutrons, and electrons in a neutral cesium-134 atom? Well, cesium, again, is right here, element number 55. So 55 here. So that tells us how many protons we have. So cesium, yes. So 55 down there and a 134 there. So whatever 134 minus 55 is, let's do some math here. Isn't that just special? And let's see. Wow, I'm drawing a blank. 7. So 79. So we have 79, and this is neutrons. These are protons, and this is both protons and neutrons. Now the key here says neutral, so we want to have the same number of protons as we do electrons. Looks like there's our winner right there, letter B. So protons and neutrons are the same because we're neutral, and we have 79 neutrons. Okay. Number 7. Which of the following molecules contains only single bonds? This could be a real time-consuming problem, and again, this technically is an organic question. However, if we can look real quickly at something like this and go, okay, well, we have hydrogen, and again, carbon always wants to have 4 bonds. Okay, whether it's a combination of 4 single bonds, 2 double bonds, 1 single bond, 1 triple bond, it has to have 4. If you can recognize right off the bat by looking at a hydrocarbon that has this combination where we have CX and then we have 2X, or I'm sorry, 3X, I believe that's right. So if we do C3, oh, I'm sorry, that's not right. It's 2X plus 2. That's what it is, that equation. So if we have like propane, C3H8, then we have our 3, so 2 times 3 plus 2. If you have that combination, those are all single bonds. You could go ahead and draw the other ones out, but you're going to have some double bonds. I know there's a triple bond in this one, 2 double bonds here when we look at these OOs next to each other. And again, I would circle this one and come back if you needed to draw them. Just remember, carbon wants 4 bonds. Alright. Yeah, and I even had circle this and come back later. Alright, number 8 and 9. Alright, here we go. Oops. It says a solution of a weak monoprotic acid is titrated with a solution with a strong base. And again, whenever we do titrations, we'll always titrate a weak with a strong. Okay, typically. We won't typically titrate a strong with a strong, but you could. But typically for AP exams, I've seen it most often with a weak something with a strong something. Alright, so consider the points labeled A through E on the titration curve that results in as shown to the right. The point at which the pH is close to that of a strong base being added. This is a really silly question. So we know that we're looking at a strong base, and if we're looking at a strong base and we overflooded the system or overloaded the system, yeah, it's going to be up here in the high pH range. So E is the best answer. But, you know, I really don't like this type of question. However, you should know what this represents and what that represents. When we talk about those 2 points, those are pretty significant. At point B, we are at the half equivalence point. The half equivalence point is when the pH is equal to the pKa of your acid. It tells you when you're halfway there. So when you're doing a titration, you can turn your liquid on real quickly, allow it to pour out quickly, and when you get halfway there is when you kind of want to start to slow down because the pH is starting to change. Technically speaking, in this area to this area here, the solution is sort of acting like a buffer. It's controlling the pH pretty well, but once it hits that point where it's about to hit the equivalence point, man, that pH just starts going crazy. So B actually represents the half equivalence point. And again, I erased it. But at the half equivalence point, the pH is equal to the pKa of the acid. Now remember what P means. P means negative log. So if you're looking at the concentration and the negative log of your Ka value, okay. Probably the most important point on our titration curve is C, and that is the equivalence point. And what does the equivalence point mean? Well, that is when we have our moles of our acid is equal to the moles of our base. Now, the key word here is moles. Or you could say moles of hydrogen is equal to moles of hydroxide. Probably better statement, because oftentimes when we talk about moles, we could have a diprotic, triprotic, or a polyprotic acid. Now again, when I talk about polyprotic, it has more than one hydrogen. And if you have more than one hydrogen, then you'll have some curves that do some things like that. And each one of these, not to scale, represents one of these situations for each hydrogen. So each bump represents a change for how many hydrogens you have. And I'll try to get one of those on a later quiz. I haven't put it on any of the quizzes yet. So this is a pretty significant point, and when we get to this point, or when we're doing a titration, we want to try to use an indicator that has a pH that is equal to the pKa of the indicator. Okay, so we want to try to get something that's in that pH, not in a pH of necessarily 7, or we may think that we're at the equivalence point too early. So half equivalence, equivalence. Okay, and yeah, we did answer that, so this should be E for 8, which is a kind of a silly question. Well, let's look at the next point. It says the point in a titration where the pKa is equal to pH. We just talked about that. That's right there, B. Okay, and it's a pretty significant reference. So when you're doing our titration, it's half of the volume has been added. And notice that we hit it right at 50, and the equivalence point's at 100. All right. Number 10. Which of the following is a nonpolar molecule that contains polar bonds? Again, make sure that you know the difference of what polar bonds are. Polar bonds, actually that means polar covalent bonds. Okay, so polar covalent bonds for AP Chemistry, if you have different nonmetals, okay, if you have different nonmetals, or if you even have different compounds for this case, because we could have ionic bonds here, and that could be between a metal and a nonmetal. However, what this is asking for as well, more significantly, is a nonpolar molecule. So when we look at a nonpolar molecule, we have to draw out the structure. So when we look at fluorine, yeah, that's a nonpolar molecule, but it has nonpolar covalent bonds. So A's out. When we look at this compound here, we have carbons in the middle, hydrogen, and 3 fluorines. Okay, so we do have polar covalent bonding on all of these, but again, polar compound, that one's out. Let's skip C for a second. Yeah, I know. Hydrogen chloride, again, polar covalent bond. Some would argue that that might even be an ionic. The difference in electronegativities don't merit that. And also that's a polar compound. And then ammonia, NH3. Okay, again, polar. So carbon dioxide is the one that we're looking for here, because it is a non-polar compound. When we look at our external atoms, there are no lone pairs on the carbon. All the external atoms are the same, therefore it's non-polar. So C should be our answer. All right, number 11. The oxidation state that is most common in aqueous solutions or aqueous ions of iron, manganese, and zinc. Now, I'll be honest with you. When we look at these metals here, iron has more than one charge. Manganese, wow, manganese has got quite a few. It's close to 4, 5, or 6 charges. However, zinc only has one charge, and you must know the charge for zinc. You actually must know the charge for silver and zinc. And there's an easy way to remember this. I call it the aluminum slide. We start with aluminum that has a +3 charge. We slide down to zinc, which has a +2. And then we go down to silver, which has a +1. So 3, 2, 1. Again, the aluminum slide. Start at aluminum, go to zinc, then to silver. 3, 2, 1. Okay. So typically all the other metals have more than one charge, and you would be given information regarding those. Now, yeah, I know that these guys have a 3 charge over here, but we don't use these elements. We don't use those elements often enough. Hopefully I don't need to use that again. So 2 should be our best answer here. Okay. Alrighty. Number 12. A compound contains 30% sulfur and 70% fluorine by mass. The empirical formula of this compound is, got to do real quick math here, and I erased the periodic table. I apologize. But sulfur has a molar mass of around 30 grams, 30.97, 30 grams per mole. So if we have a 30% and a 70%, let's just say we got 30 grams. So that means that we have 1 mole of sulfur. Okay, roughly. And then when we look at fluorine, it has a molar mass of 19 grams, so we'll say 20. So we know that this that fluorine goes into 70 approximately 3 times. But again, 38 times 2, what is that, 76? You know, it's a little more than 3, so C's our best answer. We don't want to, and luckily we don't have a SF3 on here. So our best answer would be this. Definitely would not be 2. I might wager toward an SF3, but I know too much about bonding to pick that one. Alright. Number 13. Which of the following has the same number of electrons as bromine -1? Boy, I really wish I wouldn't have. Let's see if I can get it back. I don't think I can. Daggone it. Yep, I can't get it back. Sorry, guys. We're looking for isoelectronic values here. So if you have your periodic table, take a look at bromine. And when we look at bromine, if it has a -1 charge, then we're... I need to grab a periodic table. Oh, sorry. Talks amongst yourselves while I grab a periodic table. I had a grasp on here. I'm really sorry for deleting that periodic table. But when we look at bromine, it has the same electron configuration as krypton, and so then what we want to do is -1 for krypton. I'm sorry, -1 for bromine has our electron configuration of krypton. So definitely not chlorine, since chlorine's right above bromine. Definitely not iodine, since iodine's right below bromine. Strontium +2 would. Potassium would not. That's argon. And calcium is also argon. So C should be our best answer. So again, when we talk about removing 2 electrons, strontium's right here. We lose that 1 electron from the strontium and 1 from the rubidium. And then we go all the way back up and we have the same configuration as krypton. So when we lose 2 electrons, we take them from there and there. Now it's the same as krypton. So C should be our best choice. 14. Electron configurations. Of the following electron configuration of neutral atoms, which represents an atom in an excited state? Now, you don't need your periodic table for this, but do realize that for ground state, we're going to fill up our 1s orbital with 2 electrons. Then we'll jump to the second row and fill up our 2s orbital with 2 electrons. Then we'll jump over to the 2p and put 6 electrons in there. And then once we have 6 electrons in there, then we'll jump to the 3s and we'll drop 2 electrons there. And then we'll drop 6 more electrons in our p. If one of these electrons get excited, say like maybe one of the electrons from the 3p get excited, we can get one of these electrons to go from the p into the s. That's an excited state. So we could move one ahead, but it's not going to stay there very long. So don't get excited about it being there, but do realize that that is in an excited state for a moment. So when we look at our selections here, A looks good. Uh-oh. We have a 5 there. 2, 2, 2, or 2, 2, 6, 1. That one's okay. 2, 2, 6, 2, 2. That's okay, because we only have 2 so far. And then 2, 2, 6, 2, 5. Yep, C's our excited one. So we took, I'm sorry, B's our excited one. So we took one from there and moved it into the s orbital. Okay. So again, excited means it's moved to a higher energy level, but it's not going to stay there. Now, let's also talk about what happens once an electron moves to a higher state. So we're going to put some energy into this electron. It moves to a higher state or to a higher energy level or orbital. So if it's in that orbital, it moves to this orbital. That electron's not going to remain there for very long. It's actually going to return back to its ground state. If it absorbs energy, how does it release that energy? Well, it releases it as a photon of light. And depending on how much energy and what level it jumps to, depends on, or will determine the type of color. So make sure you know your Roy G. Biv. Okay, so if we give it a lot of energy, it'll be on this end of the spectrum. If there's not so much and it doesn't jump very high, then it'll be on the red end of the spectrum. All right. 15. What is the molality of a solution of a phosphoric acid that contains 24.5 grams of phosphoric acid and has a molar mass of 98 and 100 grams? Now again, recall, molality is moles of your solute over your kilograms of your solvent. So we have solute and solvent. Okay, solute solute gets dissolved. Solvent does the dissolving. So it looks like we're dissolving 24.5 grams of phosphoric acid, and if the molar mass is 98 grams, whoa, what'd I do? Sorry. Okay, so if we have 24.5 grams of it, and the molar mass is 98, oh no, what did I do? That means that we have about 1/4. Oh, darn it. There we go. Okay, we have about 1/4 of a mole. Approximately, not exactly, or actually we do have exactly 1/4. And again, our mass is in grams, so we need to change that grams into kilograms. And if you need to show this, that's fine. There's 1,000 grams in a kilogram. So what that means is we're going to move the decimal over one place when we get rid of the grams. So we'll be left with moles per kilogram. So we should have 2.5 moles. And it looks like B. Okay, so be careful on that. Don't go too quickly, but do realize what molality deals with or represents. And again, that's way too much work, and you don't need a calculator to do all that. This should be mental math. Hopefully that's mental math, and if you need to plug that in, that's fine. All right, 16 through 17 refer to the following things here. Activation energy, enthalpy of formation, entropy, Gibbs free energy, and lattice energy. Again, activation energy, let's draw it out. So if we're looking at, say, our reactants and our products start off with a certain amount of energy. Our products finish with a certain amount of energy. That's actually the change in energy for a reaction. That is not enthalpy of formation. This would actually be the enthalpy of the reaction. Okay. Big difference. So the activation energy is the amount of energy needed to from the reactants to form the activated complex. So that's extra energy needed to get the reaction to move forward. So that's activation energy right there. Enthalpy of formation deals with calculation to determine if I'm going to take like carbon atoms plus 1/2 of an oxygen atom to form carbon monoxide. I would get values for that to determine what the delta H for my formation of that element is, or like that compound. Entropy, obviously that's randomness disorder. Gibbs free energy deals with whether something's spontaneous or not, and lattice energy is the amount of energy to keep a solid together. So 16, quantity that would be 0 for a pure, perfect crystal. Here's your hint, at 0 degrees Kelvin. Now, the only time that we'll ever have a value of 0 for anything, for a substance, at 0 Kelvin is when we're looking at the entropy value. Okay. Any other time that we're looking at a temperature for a substance, the entropy has a value. Unlike heat of formation, if I'm looking at, say, oxygen, and it's a gas at room temperature, it has a heat of formation of 0 because it occurs like that in its elemental state at room temperature. So the best answer here for 16 should be C. 17, quantity typically determined by measuring the rate of the reaction at two or more different temperatures. Best answer here, even though it's not worded very well, activation energy. Yeah, I'm not real happy with these questions either. Is that it? So yeah, 16, 17. Okay. 18, brand new question. Ooh, I like this one. The pressure in atmosphere exerted by 1.85 pressure exerted in atmosphere is exerted by 1.85 moles of an ideal gas placed in 3-liter container at 35 degrees is given which of the following expressions? Well, that's odd. All right, so we're looking at a PV equals nRT situation here. Okay, so that's our N, that's our V, that's our T, and so we're looking for our P. Yeah, we're looking for our P. All right, so since we're looking for P, then we need to move that down. So P would be equal to nRT over V. And so make sure that we change our temperature to Kelvin, so that one's out. Temperature needs to be on top, so we know that one's out. This one looks like it's flipped, so that one's out. Nope, we don't want to use that because that's in the wrong R value, so A is our best answer here. Okay. Now again, I would do that real quickly and then just go through what I did by determining, okay, once I have my equation, find out who's legal, who isn't legal, make sure you know which R to use. Unfortunately, you're not given the equation sheet for multiple choice type questions. So you have to know which R, and it's always the 0.0821 R. The only time that we use this R is for our thermodynamic stuff. So yeah, I know we used it for kilopascals, but we don't use kilopascals on the AP exam. Everything's in atmospheres. All right, number 19. And there's my answer there. Okay. I'll scroll. All right, number 19. How many carbon atoms are contained in 2.8 grams of C2H4? All right, this would definitely be a time consumer here. So we know that we have approximately 24 grams, 2 carbons plus 4 hydrogen. So approximately 28 grams is our molar mass, which is very nice. So we have 2.8 grams in 1 mole. 28 grams, so we know we're at a tenth. How many carbon atoms? So we know in 1 mole we have Avogadro's number. And again, you do not need a calculator to do this. and wants to know how many carbon atoms. So let's see, and that's how many molecules we have. So in one molecule, we have 2 carbon atoms. Okay, so we have 0.1 times this times 2. So I can real quickly, let's see, it's going to be 1.2. So we know that that's out, that's out, that's out. So now we're down to these 2 guys. And since we're a tenth and then we double it, A is my best guess. Okay, so we move the decimal place, 0.1. Do we go to the left or right? Ah, man. Good, A. Okay, so doing real quick math, probably this part right here, we have to do 0.1 times the 6.02 times 10 to the 23rd. And so that means that we'll move the decimal place an additional point over. All right, one more question on this one. I like these quizzes, I really do, and I hope that they're helping you here. On the basis of the strength of the intermolecular forces, which of the following elements would be expected to have the highest melting point? Now, the one thing that we have to realize when we're looking at a question like this is we have to ask ourselves, first of all, what type of intermolecular forces do we have? Because intermolecular forces tell us the strength of the bonds that will allow us to change from a liquid to a gas, or from a solid to a liquid, whatever the phase change is. The really crazy thing is every one of these have London dispersion forces. Every one of these. In other words, if I draw these guys out, they all have, well, these have single bonds, and this has a triple bond. However, it doesn't matter what type of bond it actually has, because it's the force between the molecules that we're looking at to change the state. Krypton, even though it's a noble gas, still has dispersion forces. So when we look at all of these things, we have to find the one that is the most massive. The most massive has stronger intermolecular forces. And if you know, by looking at the periodic table, that if we look at chlorine, bromine, and iodine, chlorine's a gas at room temperature. Bromine's a liquid at room temperature. Iodine's a solid at room temperature. And so what we have to realize is as we go down that periodic table, the molar masses are getting more and more. Therefore, the intermolecular forces are getting stronger and stronger. However, on the other side of the periodic table, as we go down the chart, say from lithium to sodium to potassium to rubidium on down, as we get more massive, the boiling point actually goes down. So it's a different, so when we look at boiling point or melting point, it's a reverse since we're flipping it to the other side. But on the non-metal side, we definitely want to look for the most massive one, and I believe it would be A. Okay. All right. Now, again, I highly recommend that you do these quizzes, watch the videos, but please, please, please watch or take the quiz before you actually watch the video. And again, as always, I hope these videos are helping. I'd like to see you get a 5 on the AP exam, and it's worth me going over these to help you get that. Tune in for more.